Hello, and welcome to this presentation on vectors, specifically looking at vector products. These vector products presentations are broken into two parts. This part relates to the theory behind the vector products and the way we use determinants to solve them, and part two will be applications of the theory, looking at examples and exercises and questions associated with vector products. This part 1 presentation does assume we've already seen the introduction to vectors presentation using analytical methods and also the scalar products presentation. The information and techniques used in those presentations will help underpin this presentation. Let's consider a vector product, sometimes termed a cross product. A vector product of A and B is denoted by A cross B, and it's essential in this presentation when we're dealing with vector products we use this cross notation. If you recall from our previous presentation on scalar products, we used a dot between vectors A and B to represent the scalar product or dot product, but within vector products we must use the cross notation between the vectors. The vector product of two vectors A and B whose directions are inclined at angle theta to each other is stated as A cross B is equal to the magnitude of A multiplied by the magnitude of B multiplied by the sine of angle theta multiplied by little n, where n is equal to the unit vector whose direction is perpendicular to the directions of both vectors A and B, in the sense that a right-handed screw rotated from direction A to direction B moves in the direction of the vector product. The modulus of vector A cross B is given as A cross B equals to the modulus of A multiplied by the modulus of B multiplied by the sine of theta. We don't use the n in this case. And the relationship between the direction A cross B and the directions of A and B are shown in figure 1 above. So in figure 1 we've got vector A drawn here, vector B drawn here, and we have angle theta between them. If we move from this vector A through to vector B in this direction, we find from the right hand screw rule that the direction of the cross product AB is in this direction. If we were to calculate the vector product of B cross A, we would effectively move in this direction of angle theta, and this would then make this the direction of B cross A. In other words, we've reversed the direction of the vector by reversing the rotation. So as stated on the previous slide, we need to be very careful about noting the rotation of the vectors, as this determines the direction of the cross product. So in figure 2 on the right hand side here shows a hand, not drawn particularly well, so you can see why I never passed my A-level art, but it does indicate how the right hand screw is applied. If we calculate the vector A cross B, then the direction of rotation is from A to B through angle theta, and using the right hand screw you notice my thumb would point upwards, so the direction of A cross B is vertically up the page. If we were to calculate the vector product of B cross A, then my hand would be reversed and my thumb would point down the page, so the direction of the B cross A vector would be downwards. Let's consider unit vectors and their vector products. We know from previous work that the unit triad ijk, shown in the sketch here, are mutually orthogonal vectors. The magnitude of vector I would be 1, the magnitude of vector j would be 1, the magnitude of vector k would be 1 because they're unit vectors. If we now consider the vector product of I cross with j, then from the definition of a vector product, that would be the magnitude of vector I multiplied by the magnitude of vector j multiplied by the sine of angle theta, which would be 90 degrees in this case, because I and j are normal to each other. So the vector product of I cross j would be 1, because that's the magnitude of I multiplied by 1, the magnitude of j multiplied by 1, which is the value of sine of 90 degrees. If you go to your sine curve and you look for the ratio associated with 90 degrees, it's 1. So So in other words, the magnitude of the vector I cross j is 1, and its direction from the right-hand screw rule would be in the positive k sense. If we apply the same principles to j cross with k, we would find the same thing. The magnitude is 1, but the direction would be in the positive I from the right-hand screw rule. If we now look at the vector product k cross with I, again the magnitude would be 1, but the direction would be in the positive j. And you can check that with your right-hand screw rule. If we consider the vector product of I cross with I, then that would be the magnitude of I times the magnitude of I, so that would be 1 times 1, but it multiplied by the sine of angle theta, which would be 0 in this case, because I and I are the same vector, so they're on top of each other, but the angle between them is 0. On our sine curve, the sine of 0 is 0. So therefore, I cross with I would give us a value of 0. Similarly, we can find that j cross with j is equal to k cross with k, and they're also 0. Let's review some properties of vector products. Property 1. The vector product of two vectors, a cross b, is termed a cross product. Property 2. Vector products are not commutative. In other words, vector A cross with vector B does not equal to vector B cross with vector A. A cross with B is equal to minus B cross with A. Property 3. Vector products are not associative. In other words, vector A cross with, in brackets, vector B cross with vector C does not equal to vector A cross with vector B in brackets cross with vector C. Property 4. For any scalar k, the following is true. K multiplied by vector A cross with vector B is equal to A cross with k multiplied by vector B. Property 5. If two vectors are orthogonal to each other, that's perpendicular to each other, their vector product is A cross B is the magnitude of A cross with the magnitude of B multiplied by the sine of theta. That's a definition of a vector product. If in our case the angle between the two vectors A and B is 90 degrees, then the sine of 90 degrees is 1, so therefore A cross B is the magnitude of A cross with the magnitude of B. Properties of vector products continued. Property 6. If two vectors are parallel to each other, so A and B vectors are parallel, then from the definition of a vector product, A cross B is equal to the magnitude of A cross with the magnitude of B multiplied by the sine of theta, but if they're parallel, then angle theta is 0, and the sine of 0 is 0. So in this case, the vector product A cross B would be 0. Property 7. If A is equal to B and angle theta is 90 degrees, then A cross with B is equal to the magnitude of A cross with the magnitude of A times the sine of 90 degrees. Sine of 90 is 1, so A cross with A would give you A squared, the magnitude squared. In the case of unit vectors, I, J, K, which by definition are at right angles to each other, shown in the diagram here, then I cross with I equals to J cross with J equals to K cross with K is equal to 0, as the angle between I and I, J and J, K and K would be 0, and the sine of 0 is 0. I cross with J, J cross with K, and K cross with I all equal to 1, because by definition those vectors are at 90 degrees to each other, and the sine of 90 degrees is 1. Property 8. If theta is the angle between two vectors, A and B, shown in our diagram here, then we can rearrange the vector product formula to read sine of theta is equal to A cross B divided by the magnitude of A multiplied by the magnitude of B, where the magnitude of A or B is found from Pythagoras' theorem applied in 3 directions. Let's consider unit vectors and vector products further. Let's consider vector product of two vectors that are in unit form. So vector A is a1i plus a2j plus a3k, and vector B is b1i plus b2j plus b3k. We're going to find the cross product of A and B. So that will be a1i plus a2j plus a3k cross with, multiplied with, b1i plus b2j plus b3k. So expanding the brackets, we will get a1i times b1i plus a1i times b2j plus a1i times b3k. So I expanded the first term in the first bracket with the three terms in the second bracket. And we could do the same for the other two terms in the first bracket. I'll let you look at the expansion there. If I tidy up the above expressions, I get a1 b1 I squared, because we've got an I times an I here, plus a1 b2 times ij plus a1 b3 times ik. And we can do that for all the terms, which I'll let you review here. So considering the vector products of unit vectors and applying the definition of a vector product here, we end up with I times the sine of angle theta. Angle theta will be 0 because I and I are the same vectors. So the I squared times the angle theta of 0 is equal to the j squared times sine of 0 is equal to the k squared times sine of 0 with equal to 0, because sine of 0 is 0 from our sine curve. If we now look at the vector product of ij, that will be ij times by the sine of 90 degrees from the definition. Don't forget I and j are mutual orthogonal vectors there at right angles to each other. And we know from the right hand screw rule that gives us 1 in the k. Similarly, j times k multiplied by the sine of 90 degrees gives us 1 in the I, and k times I times by the sine of 90 degrees gives us 1 in the j. You can check that from your right hand screw rule. And we know that the sine of 90 degrees is 1 from our diagram. Sine of 90 degrees gives the value of 1. If we note that A cross B is equal to minus B cross A, then we can also write the J times the I is equal to minus K, the K times the J is minus I, and the I times the K is minus J. We see this by applying the right hand screw rule. So if we now refer to our previous slide, what we find is by definition this term will disappear because we've got an I squared is 0. This term will disappear because we've got a j squared, so that's 0. And this term will disappear because we've got a k squared, and k squared is 0. But all the other terms are now relevant to this vector product. What we can now do is replace the various ij's and the ik's and the ji's, etc. with the unit vector values we found on this slide here. So to find how we obtain this line here, let's go back to the previous slide. So we take this term here, the a1, b2 multiplied by the ij. Now the ij vector from our unit vectors is given the value of k. So we simply replace the ij with the k here. If I take the next term, this was an ik term, so we will now look for ik. That's replaced with the minus j. And be careful here, the ik gets replaced by the j and the negative change of sign there. If I take my next term, I've got j times I for my unit vectors, so j times I gets replaced with negative k, so the k there and the negative in front. Looking at my next term, I now get the j times the k unit vectors, so j times the k is replaced with the I here, so I, and that's positive in this case. Looking at my next term, I get k times I as my unit vectors, and the product of k times I is j, so that simply gets replaced with j there. And for my final term, I've got k times j, so k times j gets replaced by negative I. So again, we get a change of sign here and an I place there. So that's how we end up with that line. So all I'm doing on the final line here is factorising on the I terms. And if you look at the line above, I've got an I component here and an I component here, a negative one there. So I'm just factorising that. So that's where the A2 B3 minus the A3 B2I comes from. If I look at the J terms, I've got a J value there, it's a negative minus the A1 B3, and I've also got a positive J there, the A3 B1. So I'll just replace them into the bracket there, if that's my J terms. And finally my K terms, I've got an A1 B2K there, and I've also got a minus A2 B1K there. So that's where that bracket comes from. So continuing from the last slide, I just repeated this vector product A cross B here, which we derived on the previous slide. Now, a vector product can be written in what's called determinant form. Now, determinants are a topic of their own, which I don't have time to cover here. I would suggest if you want to see more about determinants, look at the reference sources at the end of the presentation. There's some very good work in those books that will help you understand how determinants work and how you solve determinants. But I'm going to show you an overview of the process here, and that will be enough for you to solve these vector products. Now, one thing to note between the line above and this line here is that I've changed the sign of the second term. In other words, this sign here was positive on that line, and I've made it negative on this line. And I've reordered the terms inside the bracket because I'm basically multiplying throughout by a negative value here. So I've not affected the overall mathematical line, it still is the same value, but I've reorientated it. And if you look at determinant theory, you'll see we need this pattern. It's something called a chessboard pattern. We need this pattern to help us solve determinants in the process I'm going to show you. So for now, without referring to the additional reference sources, please accept this process of our brackets must be a plus for the I, a negative for the J, and a positive for the K. So what we're going to do now is solve a vector product of two vectors using determinants. The two vectors are labelled A and B, and we defined them previously. Notice these vertical lines here and here just indicate a mathematical notation for determinant. Column headings are I, J, K relating to the unit vectors in the three mutual orthogonal directions. And what we're going to do in this row here is to write the coefficients of the A vector. So this is A1I, this is A2J, and this is A3K. And the next row we write B1I, B2J, B3K. Those are the original values we would have from the original vectors given to us. So what we're going to do now is evaluate the A cross B vector product using determinants. And the method I'm going to show you here will be the same in all the vector product questions we're going to look at. So try and get familiar with the process, and please keep to the notation I'm using here as you apply it in other questions. So the first thing we're going to do is form the first determinant, the plus I. Now plus I is actually formed by the coefficients of A2, A3, B2 and B3. So the question is, how do we get those coefficients? Well, what we do when we're defining that first determinant I is cover up the I column. And then what you see remaining, the A2, the A3, the B2, the B3, are determinants for the I. When we form the second determinant, notice we must have that negative J here. We must have that negative J for most of the determinants. And we form now a determinant of A1, A3, B1, B3. So how do we get those values? Well, because we're looking at the second determinant, the J determinant, we cover up the J column. So you can see now I get A1, A3 and B1, B3. And our final determinant is plus K. And the plus K determinant consists of A1, A2, B1, B2. Again, how did I form that determinant? Well, I cover up the K column, and what's left is the A1, A2, B1, B2 coefficients. So what we're going to do now is evaluate each of the 2 by 2 determinants shown above. So the plus I determinant, we evaluate that by multiplying the A2 by the B3, which is this term here, and we always subtract from it the A3 times the B2. So shown here. And that process of cross-multiplying is applied in every determinant. For the second determinant, the negative j, we cross-multiply a1 times b3, so a1 times b3, and we take away a3 times b1. So take away a3 times b1. The same process as for the first determinant. And the final 2 by 2 determinant is the plus k. Here we multiply the a1 by the b2, so a1 times b2, and we take away the a2 times b1, take away a2 times b1. And that generic process shown there is what we're now going to apply in every question when we solve for vector products of two vectors. Some of the questions we're going to look at later in the presentation will ask us to find the magnitude of a vector product, and we do that by applying Pythagoras' theorem in three directions. If the vector is r, then the magnitude of r would be the x value in the I direction squared plus the y value in the j direction squared plus the z value in the k direction squared, and we square root the whole expression there. It's the same process we used for scalar products in a previous presentation. Here's the bibliography used to help generate the presentation. Some very good books, again, I would encourage you to review for further reading. I hope this presentation has been of interest to you, and thank you for viewing. I would now encourage you to look at part 2 of the vector products presentation, where the theory outlined here in part 1 is applied to examples, exercises and questions.